And in particularly, we're going to talk about characteristics of polynomial function. And unfortunately, those who are not present in this class would have to review it on YouTube channel. And also, I'm going to share the YouTube channel link in the WhatsApp group, okay? So what's so important about this paragraph? First of all, up until now, we discovered that there is such a type of functions as polynomial function. And it can be written as f of x equals a n x to the power n plus a n minus 1 times x to the power n minus 1, and all the way up to the final term in this sequence where it's a0 and x to the power 0, so it turns into 1. So this is a general notation for polynomial function. And there is such a thing for polynomial function that basically, if you have the polynomial function of a third degree, let's say it would be x to the third power. X to the third power is actually already a polynomial function, but the other terms of it are just zeros. And let's say you have this simple polynomial function x to the third power. And by adding additional terms like x squared, x1, plus 5, you're just simply manipulating the graph of the original function x to the third power. That's why in the previous class we covered all standard functions: x to the first power linear function, x to the second power parabola, x to the third, fourth, fifth power. Simple x to the power of 1, 2, 3, 4, 5. And these additions, they change our graph in a few different ways. First of all, they could stretch our graph in along the x-axis, so basically make it wider, like same graph, but wider. For example, here it would look like this, something like that. They also could be translated in x and in x-axis, so they can be just moved for a certain amount of units. So basically, if I take this graph, I move it 2 units to the right, each single point of this graph, and then I join these points, I'll get a translated function. Also, I can stretch and translate my function in y-axis in particularly, like up and down. And all of these manipulations are basically applied to standard function x to the third power. Here, what you're going to see, x to the third power minus 2x. So, and how is this minus 2x affecting our graph? That's how are we going to, that's what we're going to discuss in today's class. How these additional terms change our function. So, from this perspective, you can look on polynomial function, any polynomial function, and right away you can see what is a basic polynomial function, and you can see manipulations that were applied to this function in order to get this graph. So let's start with investigation. Carl knows that he can describe the graph of a linear function from its equation using the slope and the y-intercept. He can also describe the graph of a quadratic function from its equation using the vertex, y-intercept, and the direction of opening. Now he's wondering whether he can describe the graphs of polynomial functions of higher degrees using characteristics that can be predicted from their equations. So basically, our goal is to form unique fundamental representation for polynomial function that's going to suit any arbitrary value. So you can put any value into this formula, and you're going to get particular polynomial function. So here's several examples of changed polynomial function. First of all, take a look at graph number A. you can see that this graph is parabola that is opened upwards. Why is it open upwards? We already talked about it in the previous class. It's based off leading coefficient, the coefficient in front of the highest degree exponent. Here it's x squared, this is the highest degree. So, and we look on the leading coefficient, which is +1, right? It's simply x squared. So it's +1, parabola opened upwards. So it's curved like this. So its end behavior is positive infinity for y on both ends. Next thing, what we see, you can see that the vertex is strangely moved away from its origin, right? So basically, initial x squared parabola would look like this. It would pass through 0.00, right? Do you agree with me? But this graph is somehow translated. So it's translated certain amount of units in y-axis as well as x-axis translation. So I can see that in x, it's -2, and in y, it's roughly like 6 or 7, -7 down. But how can we see that algebraically looking at the equation? We're gonna get to that point. So here you can see some other examples of higher degree polynomials. Here's the x to the 4th power, and you can see as soon as it's odd degree polynomial function, as we discussed in the previous class, x to the 4th power is an even degree, sorry. So end behavior should be the same on both ends, and since the leading coefficient is minus, this like parabola with 2 maximum points turned downwards, facing downwards. Okay. So moving on, here's some more examples. You see inversed x to the power 3, because initially x to the power 3 would look like this, right? From left bottom to top right corner. But this is inverse because it has leading coefficient of -1. And it's also an odd degree polynomial function. So that's why end behavior is opposite, as you can see. And here, what we know up till now, we know the degree of a polynomial function based on its highest exponent. We know whether it's even or odd degree, right? We know leading coefficient, which is also important, multiple in front of highest exponent, and the end behavior. Number of turning points also can be assessed through the degree of a function. Remember that maximum number of turning points, sorry, the number of turning points for polynomial function, for example, of 5th degree would be 4. So the number of turning points is the degree -1 equals the number of turning points. So these are characteristics that we can identify up till now. And what is leading coefficient? The coefficient of the term with the highest degree in a polynomial. The coefficient of the term with the highest degree in a polynomial. I'm emphasizing on this because this is one of the crucial characteristics of polynomial functions, which may be forgotten by the student when he's writing his test, which leads to silly mistakes. And this is one of a few things that you have to do while evaluating polynomial functions. So here is another definition for polynomial functions. In its basics, even and odd degree polynomial functions, so the basic expressions like x to the 2nd power, x to the 3rd power, x to the 4th, etc., they are going to have special symmetry. They're going to be symmetrical in a certain way. For example, even functions are going to have symmetry in their y-axis. You see this parabola has like its left side mirror of its right side, right? Imagine if y-axis was a mirror. That's what symmetry is, symmetry over the axis. For odd functions, they have another type of symmetry. They have the rotational symmetry around the origin. So basically, if you mirror each point in its y-axis, like this. So for basically at 45-degree angle, you're gonna get this rotational symmetry. But as you can see, when we apply certain transformations to functions, they tend to lose their symmetry. For example, here we have quadratic function of second degree, which has neither of the symmetries. You see its origin, the vertex is offset from the point 0, 0, and it no longer has y-axis symmetry. But yet, parabola x squared will remain symmetrical over its vertex, right? We remember that. Parabola is symmetrical over its vertex, highest point of the vertex. So absolute maximum and absolute minimum. Why is it important? Because it's the greatest or least value attained by a function for all values in its domain. You can see that this point for x squared function right here, this point, is an absolute maximum for this function because it's the highest point that it reaches. For odd degree function, on the other hand, we don't have absolute maximum or minimum, right? Because range of this function is infinity, right? As much as possible to positive infinity, as much as possible to negative infinity. So, what else? Yep, but odd degree function not always don't have maximum or minimums. Sometimes they may have local maximum and local minimums, right? For example, as odd degree function of 7th degree, for example, this one is degree 7. You see, end behavior is opposite, and we have local maximums here. This is very important, that there are just local maximum. And what's happening at this point, that the tangent of the slope of a tangent line to this point, the highest point, will be equal to 0. That's how we identify this minimum or maximum points, through the tangent of the tangent line. And this tangent of this angle of a tangent line is nothing more than instantaneous rate of change of function at this point, right? This is what we learned in our first classes, which we dedicated so much time, because instantaneous rate of change at point equals tangent of an angle of the slope, right? We discussed about it. And for maximum or minimum points, this tangent value equals 0, because basically the tangent line is horizontal. Do you agree with me or not? Give me a little feedback here. Safa, Hala? Any questions up till now? Maybe I'm explaining too fast? No, everything fine? Okay, good. Thank you for the feedback. So what you're gonna do next Thank you, Hala. So what we're gonna do next is, reflecting. Why must all polynomial functions of even degree have an absolute maximum or absolute minimum? Why? Because for even degree polynomial function, we know that its end behavior is similar, right? Both ends are gonna end up or either positive infinity or negative infinity for y-axis, which means if it starts in negative infinity or positive infinity, and then it turns back to negative infinity, it means that somewhere there on its way to the end of a function, it reached its absolute value, the lowest or the highest point that this graph could ever reach. And after this point, basically graph is turning around. That's why we call it a turning point. Is that clear? That's why any even degree polynomial function should have at least one absolute maximum or absolute minimum, depending on what type, whether it's upside down or whether this parabola opens up or down. Why must all polynomial functions of what degree have at least one zero? So what we know about polynomial function of odd degree, that its end behavior is opposite. One side is in negative infinity and one side is in positive infinity all the time for odd degree function. Which means if this function starts in one infinity and ends up in another infinity, it means that somewhere in between, it was supposed to cross the x-axis. It's not possible otherwise, which means odd degree polynomial function would always have at least one zero. I hope that's clear. Can the graph of polynomial functions have no zeros? Absolutely, yes, because only even degree function may not have zeros or may not have values when x equals 0, in other words, because even degree polynomial function reaches its maximum or minimum value at some point. And this minimum or maximum point could be simply located above the x-axis or below it, so the graph never crosses it. Of course, if our graph goes like this or like this, any other way, then it has 0. But in general, there is a scenario when it may not be 0. And for example, parabola opens upwards and it is above the x-axis, or opens downwards and it's below the x-axis. What questions do we have? Examine all the graphs you have investigated and their equations. Is it possible to predict the maximum number of zeros that a graph will have if you are given its equation? So it is actually possible to predict the maximum number of zeros that the graph will have with a certain accuracy. And we're going to talk about it a little bit later. If you look at the graph, you can notice that not all the same functions have same number of zeros. For example, this fourth degree polynomial function has 4 zeros, and this fourth degree polynomial function has no zeros, right? It's above the x-axis. So how could we predict it? That's the question. First of all, let's make a little practice here. Just make sure we understand each other. Oh, hello, Rana. Welcome to the class. Hello, Muhammad. So describe the end behaviors of each function the possible number of turning points, and the possible number of zeros. Use these characteristics to sketch possible graphs of the function. So we have to focus on the end behavior of each function, the possible number of turning points, and the possible number of zeros. Use the characteristics to sketch possible graphs of the function. Here you can see that they applied method of try and error, and they showed that there are many different types of graph with the same properties with respect to their end behavior, number of turning points, but they all do not share same zeros, right? Please, what I'm asking from you and everybody who just came to the class, read through the solution A by yourself, because I believe the best work is when you look through the material on your own, not just the teacher tells it to you in the same voice tone. So please try to apply what we just learned to analyzing this problem. Describe the end behavior of each function, the possible number of turning points, and the possible number of zeros. Use these characteristics to sketch possible graph of the function. And here is example A. I strongly encourage all of you to focus on this now. Okay? Those who just joined may ask their questions so you can catch up with the rest of the class. So you have, let's say, 10 minutes to prepare your questions, look into it, and let's call it a short break for everyone, okay? We will see about the next test, Muhammad. I'll let you know in advance. So if you are ready, I'm ready. Boys and girls, let me know if you're back so we can continue. Okay, so I hope you had enough time to look into this solution. No, but let me walk you through it. So looking into form function in question number A, we can see that it's an odd degree function, which has a highest exponent of 5, right? Hope everybody can see it well, so I enlarge it. So highest degree is 5, so it's an odd degree polynomial function. Also, it means that it has an opposite side and behavior. So one side should be in positive infinity and the other one the opposite, respectively. So also you can see that the leading coefficient here is -3, right? Not just minus, but -3, okay? If it was simply minus here, it would mean that the leading coefficient is -1. This will be important for us a bit later. But for now, let's see it as negative leading coefficient, which means that this is basically going to be the inverse of standard third degree polynomial function that we know that looks like this. All right, so it's going to be starting in positive infinity for y and ending in negative infinity for y, as you can see it here. When x travels to negative infinity, y travels to positive infinity. When x travels to positive infinity, y travels to negative infinity. In case if the leading coefficient is positive, these signs are same. Okay? If the leading coefficient is positive. So basically our polynomial function of fifth degree gonna span from the second quadrant to the fourth quadrant, second quadrant to the fourth quadrant, right? Positive infinity, negative infinity. And this is just general representation how it's supposed to look like. Simplest case, right? But we don't have a simple function here. You can see it has much more terms in it. So it can also be having two turning points. It can also have 3 turning points, you see, or even 1, 2, 3, 4, as much as 4 turning points, because number of turning points, the maximum number of turning points, is 1 less than the degree of this function, and this function is fifth degree. Here is 4 turning points on this drawing. On this drawing, 4 turning points. We have another 4 turning points, but in another configuration. They're positioned a little bit different. And one more way of doing it. So what we did, let's look it through. In first case, what happened? If x is a very large negative number, such as -1000, negative 3x to the fifth power will have a large positive value and will have a greater effect, right? It's going to be positive because negative 1000 to the fifth power is negative number, and minus in front, minus times minus gives us plus, right? So we'll have a large positive value and we'll have a greater effect on the value of the function. It will have a greater effect because its exponent is highest. Remember, highest exponent has the greater effect in the function. Therefore, the graph will pass through the second quadrant for very large positive values of x, and negative 3x to the fifth power will have a large negative. Will have a large negative value. Therefore, the graph will extend into the fourth quadrant. Okay, using the end behavior of the function, we can sketch the possible graphs of a fifth degree polynomial. To pass through the second quadrant and extend it into the fourth quadrant, the graph must have an even number of turning points. Okay? To pass through the second quadrant and extend into the fourth quadrant, the graph must have an even number of turning points. Seems reasonable. Turn around once, turn around twice, heading the same direction. That's why it must be at least 2. Or none, as in this example, no turning points, always decreasing function. Since the function is a 5th degree polynomial, it must have at least 1 zero and no more than 5 zeros. Okay, 4 maximum turning points, but no more than 5 zeros. Maximum number is 5 zeros for 5th degree polynomial function. So one more property that we discovered now. Exponent, the greatest exponent of your polynomial function, also gives you the maximum number of zeros of this function. So basically, for 5th degree polynomial function, you have, depending on its configuration, you can have as much as 5 different solutions when x equals 0. You'd have y1, y2, y3, y4, y5, maximum number of possible solutions. Okay? This function may have 1, 2, 3, 4, or 5 zeros. Same for the example number B, letter B. Here we have even degree polynomial function with positive leading coefficient, which means an end behavior would face towards the positive infinity on both ends. And yeah, that's what we can say about end behavior. And it can have as much as 4 zeros and 3 turning points. Even degree polynomial function should have odd number of turning points in order to end up in the same direction, right? Because turn around once, okay, turn around once, turn around twice, turn around 3 times, we end up in the same direction, right? Using the end behavior of the function, sketch possible graphs of the 4th degree polynomial. To start in the second quadrant and end in the first quadrant, the graph must have an odd number of turning points. Since the function is a 4th degree polynomial, it may have anywhere from 0 to 4 x-intercepts. Remember, even degree function may also not have any zeros. Okay? And the same reasoning about why it spans from second to the first quadrant, from positive infinity to positive infinity, because the leading term, x to the 4th power, has the greatest impact, and whether it's positive or negative defines where the function is going to tend to travel at its ends. But if it's positive, it will travel upwards. If it's negative, it will travel downwards. Any questions about that, how to sketch or analyze polynomial functions based on their leading coefficient, degree of their exponent, thus number of turning points, and number of zeros, etc. And behavior. Any questions about any of those things? No questions? Okay. So reasoning about how given characteristics fit particular function. What could the graph of a polynomial function that has range y, e, r, y less or equal to 10 and 3 turning points look like? What can you conclude about its equation? So first, what we're giving is, we're giving with the range of this function. We know that on coordinate axis, this is y-axis, this is x-axis, y value would be less or greater than negative 10. Oh, sorry, just 10. Less or equal to 10. So which means 10 is also the maximum point of this graph, right? Yes? And it also has 3 turning points. three turning points. Which function has these characteristics? Even degree function has this characteristic. So our reasoning is we have a polynomial function of an even degree that has maximum point at x, y equals 10, and has an end behavior in negative infinity for both ends, right? But we also know that it has three turning points, so it won't be simple parabola. It will be something like this. 1, 2, 3. Something like this with two peaks. One of them would be the absolute maximum value, 10. So we know that we have three turning points, and we know that in order to have three turning points, the degree of this function should be greater than 3, right? And should be greater by 1, at least. So function of 6 degree, 4 degree, 8 degree will fit it. Any of these polynomial functions of degree 4, 6, 8 are even degree functions, and they can have up to 3 turning points. They can have as much as 3 turning points. That's my reasoning. So, end behavior of the function. Since the range has an upper limit, both ends of the function extend downward toward negative infinity. In the third and fourth quadrants, for this to occur, the leading coefficient in the equation must be negative. This is what we came up with together. The function has at least 2 zeros. Because the function has a maximum value, that is possible that both ends extend downward, the function must cross the x-axis at least twice. That's reasonable because its maximum value is above x-axis, right? 10. And in order to reach this point and then bounce of it and go down, you need to cross the x-axis at least twice, if not more time, right? This function has at least 2 zeros. Since the function has an absolute maximum, it must have an even degree. This is confirmed by the end behaviors because they're same. The function has an even degree. It is not possible to be sure about the degree of the function, but the degree must be at least one more than the number of turning points. This is exactly what I told you. The degree of the function is at least 4, right? Does everybody agree with my reasoning? And here is 3 examples how this function may look like. And you can see that all of these examples, as soon as this maximum point is y equals 10, all of these examples have a right to exist with respect to the given description. So for same characteristics, there would be a multiple polynomial functions that may fit into them. Okay, any questions about that? And finally, the summary. The key ideas. Polynomial functions of the same degree have similar characteristics. The degree and the leading coefficient in the equation of a polynomial function indicate the end behaviors of the graph. The degree of a polynomial function provides information about the shape, turning points, and zeros of the graph. What do you need to know? That end behaviors, an odd degree polynomial function has opposite end behaviors. If the leading coefficient is negative, then the function extends from the second quadrant to the fourth quadrant. And that is, as x travels to negative infinity, y travels to positive infinity, and as x travels to positive infinity, y travels to negative infinity. If the leading coefficient is positive, then the function extends from the third quadrant to the first quadrant. That is, as x travels to negative infinity, y travels to negative infinity, and x travels to positive infinity, y travels to positive infinity. An even degree polynomial function has the same end behaviors. If the leading coefficient is negative, then the function extends from the third quadrant to the fourth quadrant. That is, as x plus minus infinity, y travels to negative infinity. If the leading coefficient is positive, then the function extends from the second quadrant to the first quadrant. That is, x travels to plus minus infinity and y travels to plus infinity. Okay? Turning points. A polynomial function of degree n has at most n minus 1 turning points. So this first thing to remember. Turning points, n minus 1. Simple thing to remember, but I'm telling you, it's going to make your life easier. Number of zeros. A polynomial function of degree n may have up to n distinct zeros. Distinct zeros means n different zeros. Okay, the polynomial function of what degree must have at least one zero. That's correct, because of end behavior. It starts on one side and ends up in the other. A polynomial function of even degree may have no zeros. Remember, because such function can be positioned above the x-axis or below it completely. And finally, the symmetry. Some polynomial functions are symmetrical in the y-axis. These are even functions, where f of minus x equals f of x. If basically what it says, if you substitute same value of x but with minus into your function, and your function still has the same value, it means you have the y-axis symmetry. Okay? So even some strange function like x to the fourth power plus x to the second power, even we can put 2 or 5 here, whatever. This function is going to have a symmetry over the y-axis, because no matter what x value I put in, positive or negative, outcome is the same. Whether I put plus or minus 1, I'm going to get the same output. So y-axis symmetry. Some polynomial functions have rotational symmetry about the origin. These are odd functions, where f of minus x equals minus f of x. So basically what it says, that if you substitute the negative x into your function, your output would be equivalent to the minus of the positive input. So basically you would simply make your function negative if you substitute a negative x value. That's the only thing that would change. Most polynomial functions have no symmetrical properties. One more thing, I want to clarify it. Not negative, but opposite to the initial one. For example, f of x could be minus 5x squared, then minus f of x should be equal to 5x squared. This is example of non-symmetrical function over the origin, and it's reasonable because quadratic functions are not symmetrical over the origin. They're symmetrical over the y-axis. Most polynomial functions have no symmetrical properties. These are functions that are neither even nor odd, with no relationship between f of minus x and f of x. So basically what it says, if neither this or this equality fulfilled, then our function neither odd or even. Okay? If neither f minus x equals f of x or f minus x equals minus f of x are true, then our function not even, neither odd. Okay? Please take a moment to copy down some of these key points about well, these 3 points are important, and turning points, number of zeros, and symmetry. Please copy this down, and right after that, I want you to practice this one thing. I would like to ask each one of you to write your answer in a chat. This is for your classroom activity. I'm reminding you that your class activity is evaluated as part of this course. and it has a value in your final mark. So by this small activity together, you can secure your mark, and I have a good proof that you're paying attention. So A, let's say Hala, B, Muhammad, C, Rana, D, Safa. I don't know, Ahmad, do you want to solve 1, 2? The rest of you guys, Hala, Mohammed, Rana, Safa, could you please answer this question? State the degree, leading coefficient, and the end behavior of each polynomial function with respect to your letter. Hala, Mohammed, Rana, Safa. Everybody can hear me? Please, Mohammed, write your answer as a single message, okay? So it won't be spread all over the chat. Okay. Nice. I can see 3 answers here. No answer from Rana. Okay, let's start with first one. Column. Degree 4, coefficient -4, same and behavior cause it's even. Absolutely right. But which direction would it be, Hala? It's same and behavior, but is it positive or negative infinity? Down. Absolutely right. Good job, Hala. Thank you. Check mark. I can do like this. Okay. B is for Muhammad. Degree is 5, yes. Leading coefficient is 10. Sorry, Muhammad, why do you think that the leading coefficient is 10? No, a leading coefficient is not the biggest number. Leading coefficient is the coefficient in front of the greatest exponent. So you're looking into the number in front of the greatest exponent in your polynomial function, because your greatest exponent has the most impact into the function. That's why leading coefficient is that important. So here it's 2, but no problem, you got it. And behavior is f of x approaches negative infinity, x approaches negative infinity. It's usually preferred to say in another order as x approaches certain value, because x is our independent variable. So we say as x approaches negative infinity, then what happens to the y value? As x approaches to the negative infinity, so let's say x negative 1000, then your function x negative 1000, negative 1000 with the greatest exponent raised to the 5th power, negative number, some big number raised to the 5th power would still be negative because this power is odd, right? This is an odd degree function. So it will be big negative number. So when x travels to negative infinity, y would travel to negative infinity. And you're absolutely correct about it. But preferably to say as x approaches negative infinity, f of x approaches negative infinity. Good job, Mohammed. Thank you for your work. Thank you for your cooperation. Check mark. Then Rana, unfortunately, we have to skip, and moving on to Safa. Degree. Ooh, it's a tough one. But degree 4, right? So you understand that when you look here, you can see that you have 4 different terms. And when you open the brackets, first thing you think is that you're going to have x to the power 4 greatest exponent. Good job. Leading coefficient is 24. Yeah, after opening up all the brackets, I believe you can get it. But you can see that yet this is a polynomial function, right? But it's written in another way. It's factored form of a polynomial function. This is one of the forms that we have to learn, because this form gives us all of the zeros of this function. So we know that y equals 0 when at least one of these brackets equals to 0, right? Because we're multiplying them. And when one of them equals to 0, for example, x minus 5, when x equals 5, f of x, the whole function f of x, equals 0, because x minus 5 will equal to 0. 3x plus 2, same stuff. X equals 3x equals negative 2. X equals negative 2 divided by 3. This another x-intercept. 4x minus 3, the same way around. So you say that the leading coefficient would be 24. 10 times 5. So what we can do, we can just multiply 2x times x, because this is what increases our exponent. We're gonna get 2x squared. Then multiply 2x squared by 3x, because that's the next improvement that we can get. It would be 6x to the third power. Then 3x times 4x. That would give us 24x to the fourth power. Absolutely right, Safa. Because all other combinations would give us least power of the exponent. Do you agree with me or not? This combination out of all, definitely the highest. And behavior, it is neither odd or even, and it rises to the left and rises to the right. So we can see that the leading the greatest exponent is 4. So the function is even degree. It means that the ending behavior would be same. As soon as the leading coefficient is positive, it means both ends should be upwards, right? And it's fourth degree, like so. Something like that. So end behavior, positive infinity for y-axis on both ends. Rises to the left and rises to the right. Absolutely right, Safa. Good job. You had the hardest question, so you're gonna get a star. You got it. Yeah, absolutely right. Good job. So there are no such complicated examples here for you. I'm going to include some of them into your home assignment just to strengthen your understanding. I'm going to include some of the tricky questions. And I suggest we touch the next class a little bit, the characteristics of polynomial function in factored form. This is what I talked just now in the example that Safa solved. When we have this form of polynomial function, when it's written in a factored form. This is why I talked into it more deeply. So basically, what is the relationship between the real roots of a polynomial equation and the x-intercepts of the corresponding polynomial functions? So what are the real roots? So looking into this particular example, we have one quadratic function and one linear function. What you may ask me, what's similar between them? It may not be so obvious from the first view, but in reality they share their x-intercepts. So when y equals 0, if we solve both of these functions as an equation when left-hand side equals to 0 and find the x values, we're gonna see that f of x, where it's quadratic function, has x1, which equals to -2, and x2 equals to 6. We have these two roots of this quadratic function. These are 2 points where it intercepts with the x-axis. And as well for linear function, here we have only one point because it's linear function. So one solution basically, if you prefer, is going to be x equals 6. And this is the point that both of these graphs are sharing the same x-intercept. And what we can see here that we basically have the same basics here for x minus 12, but here 2x minus 12. But here we have an additional term x squared. So it brings us to the idea that all of these functions, they're somehow related. They're somehow related through some basic relation that will describe all polynomial functions in arbitrary values. Basically, what I'm talking about is a family of polynomial functions. It's a set of polynomial functions whose equations have the same degree and whose graphs have common characteristics, right? We already defined some of those characteristics in the previous chapters. For example, one type of quadratic family has the same zeros or x-intercepts. Here on this image, you can see graphs of a quadratic function that all pass through two same points, through two same x-intercepts. Take a moment to realize it. Here, you can see two terms in these brackets that are basically generalization of the factored form of a quadratic function. Any quadratic function of a second degree can be expressed as two brackets, as product of two brackets, times some coefficient. And if we have certain coefficient here as a constant value that is defined like -2 and +3, these two values are going to define basically our x-intercept for all other possible combinations with this k factor. For example, blue parabola that is facing upwards has k value equals to 5, so it's positive. This is a leading coefficient that we are so interested about. This leading coefficient is positive. Here you can see another function that has this leading coefficient just a little less. It equals to 3. And you can see how this curve deflects. So basically, I can tell that the blue curve raising faster at a faster speed than the green curve. And there is the red curve where k factor equals 15. Here, whereas the function changes its value rapidly. Instantaneous rate of change for this function is higher at any point. Of course, except for tangent value. Also, we have example of negative leading coefficient, -2, which gives us upside down parabola, as we may have already seen in a previous class. So we'll form a general notation for, in this case. In this example, B, you can see that we're creating the cubic function from the family of polynomial functions. Cubic because we have 3 terms that are multiplied by each other. In each term, we have one independent variable, x, and we have minus some constant value p, q, r. So for example, if r equals 5, this bracket would be x minus 5. Okay? And of course, a leading coefficient. You can substitute any values in this notation and you will get some type of cubic function. You can go ahead and try it in an online calculator or graphing software, but you can simply say P equals 5, Q equals 3, R equals -2. You substitute those values into this formula. You choose some leading coefficient A, let's say 1000. And you're going to see that this function of 3rd degree is going to be something like this, because leading coefficient is positive, but it's going to have 3, if it has like 3 terms like this, and all of this QR, QP are not same. P does not equals Q, does not equals R. If this implies, then we have 3 different x-intercept, right? So it means our function won't be just a slight curve, but it rather have some intersections with the x-axis. 3 intersections. 1, 2, 3. Something like this. You see, I have 3 x-intercept. In the red color. And this graph would be extremely steep in every moment that is possible to it, because leading coefficient A would be a big number. Take notice that before, when graphing calculators, there would be a note if they're not allowed. Why not? We have we have problems where we can use graphing calculator in order to solve them. But usually your problems on test do not require a graphing calculator from you. Okay, so take a notice that when Safa was solving her example, just a little bit above here, this one, she didn't have an exactly clean cubic function. She actually had 4th degree function here, right? Because x stands here, but it stands here like that only because it's minus coefficient. So basically it was x minus k something, and this k simply equals to 0. That's why we have 2x multiple like this in front of it. Also 3x in front of 3 in front of x here does not make it complete factored form, because in a complete factored form, as we can see afterwards, in a complete factored form, x is separated from any constant multiples, in the bracket, and all the constants are brought outside as 1a, leading coefficient. That this is a leading coefficient that we are always looking into. So order, the exponent to which each factor in an algebraic expression is raised, for example, f of x equals x minus 3 to the second degree times x minus 1, the order of x minus 3 is 2, and the order of x minus 1 is 1. So this bracket would have more impact into the solution. And also order, the higher exponent comes first. That's what order implies. Okay, and I think that's it for today. Because I don't want to overwhelm you with polynomial functions. Just solve few examples at your homework, and in the next class we'll continue from the same spot. Thank you for your